All right, so this is going to be one of the first problems we work using direct integration. And the first thing I want you to notice is, remember, the relationship we had for displacement was the double integral of m over EI. And what's going to make this process work really well is if we can write a single continuous function for moment. That means we can integrate it across the whole section. So the first question you have to ask yourself is, can I write an equation for moment over the length of this structure? And I'll also add on that we're going to assume x goes from left to right. So can you do that? The answer is yes, you can. So first thing I'm going to do is do that. So I'm going to come here and I'm going to assume that I have a positive shear force at A and a positive shear force at B. And I'm going to cut this structure eventually, say here, and probably to make it easier on myself, I'm going to look at the left-hand side. So to do that, to use my free body diagram to find my moment here as a function of x, I just need to find my reaction at A. So to find my reaction at A, I'm going to sum moments at B. We're going to sum moments at B, make sure we're in equilibrium. I'm going to use right-hand rule for my sign convention. So the first thing I'm going to want to do to help me find my reaction at A is to take this distributed load, which is a little complicated to deal with, and we'll just come up with a concentrated equivalent of it. So to make sure the two magnitudes match, the magnitude of my equivalent force will be the area of the curve. It's a rectangle, so the area is base times height, so that'll be WL. And the distance will be the total length, L over 2. So I know where its position is. So when I'm summing moments about B, then I'm looking at the moment created by the concentrated equivalent. That's going to be positive or negative moment. I'm using right-hand rule. That's going to be positive. So I'm going to have a force of WL times a moment arm of L over 2. So that's the moment, effective moment of the distributed load about B. And then reacting that will be the moment associated with the shear at A. And that's going to create what kind of moment about B? Positive or negative? Negative, right? And then its moment arm is L. So the shear at A should be equal to WL over 2. Okay? Basically half the load. So now I'm going to come back. I'm now going to cut my structure at some distance x. I know my shear force is WL over 2. And then I'm going to look at this section of the curve, the distributed load. We know it has an intensity W. And at the section where I cut it, I'm going to look at positive shear and positive moment. Now remember, all we care about here is the moment, so we don't really need to worry about the shear right now. So just like we did up here, I'm going to work with the equivalent force of the distributed load. And again, it's still a rectangle, so I know my distributed force magnitude will be the base times the height, which will be a force of Wx. And the distance from the cut to the centroid, that's the total distance x divided by 2. And I'll just write that in there as x over 2. So now I'm going to write the equilibrium equations for this section to solve for moment. So again, I'm going to sum moments, assuming right-hand rule for my sign convention. And I'm going to sum my moments about the cut I just made and make sure this section's in equilibrium. So let's see what I've got. I've got the moment, which according to this sign convention is positive. About the cut surface, this equivalent force creates what kind of moment? Positive or negative?
Positive.
Positive. So I've got a positive force of Wx, and the moment arm is x over 2. And then I have the moment created by this reaction force, this shear at A. That creates what kind of moment?
Negative.
Negative. So that force is WL over 2, and its moment arm is x. So I can solve for the moment. The moment is equal to what? Well, I'll throw everything to the other side of the equation. So this is Wx squared, that's negative. So it's Wx squared over 2 plus WLX over 2. Now we can stop, just like we did in the first part of the course, we can stop and make sure this looks okay. Now we do know the moment someplace. Where do we know the moment? Do we know the moment at A? Yeah. So I know that the moment at A, which is at x equals 0, should be 0. Well, is it? Well, you put an x equals 0, this term is 0. Put an x equals 0, this term is 0. Yeah, that's right. It works. What else do we know? What about at B? We do know that too. So we know the moment at x equal L should also be 0. Well, is that true? If I put it in here, L, I get WL squared over 2, negative, plus WL squared over 2. Cancels. So that also is true. So at this point, you should be pretty confident you got the right moment. And this is where we'd have stopped on exam 1, if you were so lucky you have to get this problem. Well, that's not true. You'd have to go ahead and get the shear. But you could just take the derivative of the moment equation and get the shear, right? So now that's part 1. Part 2 is what? We need to plug that into here. So the first time we do it, put a little divider. We're going to say the slope is equal to the integral of the moment divided by EI. So let's do that. Let's look at our moment equation. Every term in the moment equation has a W and a 2. So I'm going to pull those out. Right? And we'll assume that EI is constant. So I'm going to end up with W over 2EI. And then I'm going to have the integral of what's left over in the moment expression, which is minus x squared plus LX. No, the x's have to stay in the integrand because that's what we're integrating on. You could pull one out of there, but I don't think that helps you any. So now this is a pretty simple polynomial to integrate. So I'll keep my constant the same. So I'll have W over 2EI. And then I'll get minus x cubed over 3, that's the integral of the first term, plus Lx squared over 2, that's the second term, plus now our first integration constant. Now you have to ask yourself, do I know anything about slope so I can satisfy this constant? Now if you look at just the points that you're sure about, A and B, you don't know anything about slope. You know the displacement at A is 0. You know the displacement at B is 0. The slope there is not 0. But you know somewhere out here, the slope is going to be 0 where the displacement is maximum. Where do you think that might be? Well, for this problem, simple supported beam, uniform load, it's right in the middle. But I'm not going to do that right now. I'm going to say, I'm not really comfortable with doing that, at guessing where the slope would be 0. So I'm just going to leave this alone. So now when I go to a displacement, I'm going to integrate my slope. So I'm going to integrate this thing. Well, again, W over 2EI is a constant. So let's integrate these terms. So I'll integrate this one. I'll get minus x to the 4th over 12 plus Lx cubed over 6. What's the integral with respect to x of C1? C1x. And then a new integration constant, call it C2. Oh no, what am I going to do? Well, I have an equation for displacement, but I have two displacement constraints, right? I know that the displacement at x equals 0 is 0. So what if I put x equals 0 in here? 0, 0, 0. What am I left with? All I'm left with is C2. So C2 has to be 0. That wasn't too bad. I also know that the displacement at x equal L is also 0. So let's evaluate this at x equal L. So I put L here. I got L to the 4th over 12, L to the 4th over 6. Right? If you make that a common denominator of 12, what do you get? You get L to the 4th over 12. You guys see that? That's this evaluated L. What's C1 times L? C1 times L. You see that? So what does C1 have to be equal to? If this is 0. Minus L to the 4th over 12. Oh, L to the L cubed. That L cancels one of those. See that? So I just plugged in x equal L into my equation and forced it to be 0. Now one thing I have messed up on is I forgot my constant here. So actually this whole thing needs to be multiplied by W over 2EI. Because this term really should be W over 2EI times L to the 4th over 12. I messed up. You see that? I forgot to bring my constant along when I evaluated that. So all I have to do is stick C1 back into there, and I'm done. So what would be my displacement equation? Well, I still got the W over 2EI out front. And then inside I have what? This minus x to the 4th over 12 plus Lx cubed over 6 plus C1x. And there's C1 with the same constant, so that'll be minus L cubed x over 12. So I now have an equation for displacement at any value x in the beam. And you notice that each of the terms have the same order. See, that's length to the 4th, length to the 4th, length to the 4th. Pretty cool, huh? And I could also plug C1 into here and have a displacement for slope, or have an equation for slope. Let's see if I can squeeze that in here. So let's see, what do I get? So I've got minus x cubed over 3 plus lx squared over 2 plus c1, which is minus l cubed over 12. We also know that the derivative of displacement should be equal to the slope. If I take the derivative of displacement, do I get the slope equation? Yes, I do. Now, where would the maximum displacement be? What do we know about displacement? It's usually a local minimum or a local maximum, right? And those are always defined as the slope going to 0. So all I'd have to do is find where this equation is equal to 0. It looks kind of challenging because it's a cubic equation. Finding the roots of a cubic equation might be a little tricky. But it's not as bad as you think. And then once you found that position, you would plug it in here for x and you could find the displacement. We probably already are comfortable that L over 2 is where that's going to happen. So what do you think? Any concerns about this before we move on? I like this problem because it's very mathematical. You don't really have to think so much. Once you get your moment equation, you just integrate it twice. Evaluate your constants. Integration is pretty straightforward. You guys should be pretty good at integration by now, especially a polynomial. So the really structural mechanic oriented things are coming up with the moment equation correctly and checking it if you can, and then your two conditions on displacement and slope that you need. And that depends on the problem. So what do you think? Exciting stuff, isn't it? So you can see how your skills from the first part, being able to write moment equations, are going to be right back again. So you'll just continue to get practice doing these things. And by the time the final rolls around, that first part of the final, which would be the exam 1 material, is going to be pretty, should be pretty comfortable with it. Okay, well, I'll stop here.